The transition from direct current to alternating current was driven by the need to transmit electrical energy efficiently over long distances. Pioneers like Nikola Tesla built massive induction coils to harness alternating currents, allowing voltage to be easily stepped up or down. To control these alternating currents, engineers rely on the series LCR circuit. It is a configuration containing a resistor, an inductor, and a capacitor wired in a single loop to an AC voltage source. Because this is a series circuit, it follows a strict rule. The current flowing through every single component is exactly the same at any given moment. But there is a strange mathematical anomaly. If you measure the peak voltage across the resistor, the inductor, and the capacitor individually, and add those numbers together, the sum does not equal the total voltage supplied by the source. This discrepancy occurs because the three components do not reach their peak voltages at the same time. While the voltage across the resistor might be maxing out, the voltage across the capacitor could be hitting zero. Since these voltages are out of sync, we cannot add them together like simple numbers. We have to treat them as quantities that possess both a magnitude and a specific direction in time. To visualize these out-of-sync voltages, we use a tool called a phasor. A phasor is a rotating arrow, or vector, that represents a quantity oscillating at a constant angular speed. Watch the vertical height of this rotating arrow. As it spins, that height goes up, drops to zero, goes negative, and comes back up, perfectly tracing the shape of a sine wave over time. If we freeze these rotating arrows at a specific instant, we stop the movement. This allows us to analyze their relative angles, or phase differences, without the distraction of motion. The length of the arrow itself stays constant. That specific length represents the absolute peak amplitude of the oscillating voltage. By turning a time-varying wave into a fixed rotating line, the phasor translates complex calculus into basic geometry. Since current is identical across all components, we use it as our horizontal reference. Resistors don't delay current, so their voltage points in the same direction. Inductor voltage leads current by 90 degrees, pointing straight up. Capacitor voltage lags by 90 degrees, pointing straight down. Inductor and capacitor voltages point in opposite directions, putting them in a state of constant cancellation. We simplify this tug-of-war by subtracting one from the other to find net vertical voltage. Combining the two vertical vectors leaves a single net vertical line, representing the total reactive voltage. We connect this line to the tip of the horizontal resistor vector to form a right-angled triangle. Drawing the hypotenuse from the origin reveals the source's total voltage. By applying the Pythagorean theorem to this right triangle, the total voltage equals the square root of the horizontal squared plus the vertical squared. The voltage that seemed to be missing when we simply added the numbers was actually never gone at all. It is locked in a geometric relationship that accounts for exact time delays between components. This triangle also reveals how the circuit restricts current flow entirely, a property known as impedance. Impedance is the total equivalent resistance of an AC circuit, accounting for both standard friction and time-delayed reactance. If we divide every side of the voltage triangle by the current, we scale it down into the impedance triangle. The horizontal base becomes resistance, the vertical side becomes net reactance, and the hypotenuse becomes the total impedance, labeled Z. This provides the master formula for the circuit. Impedance equals the square root of the resistance squared plus the net reactance squared. The angle nestled between the resistance and the impedance is the phase angle. It tells engineers exactly how much the circuit's total current is leading or lagging the source voltage. Impedance is the mathematical bridge that allows engineers to treat a complex system of inductors and capacitors as a single quantifiable unit of resistance. If you vary the frequency of the AC source, you reach a point where the inductive and capacitive reactances perfectly cancel each other out. This specific condition is called resonance. At resonance, the circuit's total opposition drops to its absolute minimum, leaving only the standard resistance. Because the opposition is so low, a massive surge of current flows through the circuit. Think of a child on a swing. By timing your pushes to match the swing's natural frequency, you build up a large amplitude of motion. When a circuit is driven by an energy source near its natural frequency, the current amplitude maximizes in the same way. This exact mechanism is used to tune a radio. By turning a dial to adjust the capacitor, you match the circuit's resonant frequency to a specific radio station. absorbing energy from that one frequency while rejecting the others. The LCR circuit is a highly selective filter. It relies on the geometry of phasors to pull precise, targeted signals out of the chaotic electromagnetic noise of the modern world.